Well, friend, I would like to welcome once again to this refresher course on fluid flow and hydraulics. So, in the last few lectures, we have mainly discussed about gradually varied flow. So, what is gradually varied flow? And then we discuss how we can compute the gradually varied flow profile. So, we discussed the graphical method, then some numerical method. So, today we will discuss another topic, and this is your spatially varied flow. Okay, so we'll discuss. So we'll derive the governing equation for spatially varied flow. Now let us see what is spatially varied flow. Okay, the spatially varied flow has a non-uniform discharge resulting from addition and reduction of water along the course of flow. Okay, so what does it mean? That if there is an open channel. So, if there is an open channel, so if there is some your addition of flow from the side or from the bottom of the channel, so or there is a reduction, then this is the flow is varying spatially in this direction. So, flow is varying spatially here, and in that case we call it spatially varied flow. So, it may be that the water may be added to the channel. So, in that case the discharge is increasing, or water may be reduced, so due to your infiltration or side wear. So, in that case this is spatially varied flow with decreasing discharge. Okay. So, now the addition or the reduction of water will cause disturbance in the energy and momentum content of the flow. So, whatever water is entering or whatever water is coming out of the channel, so it will disturb the energy and momentum content of the flow. So, therefore, that has to be considered in deriving the spatially varied flow equation. So, as such the Hydric behavior. So, because of this addition and reduction of water, the Hydric behavior of spatially varied flow is more complicated than that of flow without with your constant discharge. So, the Hydric behavior of spatially varied flow with increasing discharge and is different that of your decreasing discharge. So, what we are basically discussed that. So, as I said that the flow may be increasing. So, there is a addition of flow into the channel. So, the behavior of that particular channel will be different when there is a reduction of flow from this channel. That means, water is coming out of the channel. So, in that case the behavior of the Hydric behavior will be different. So, that we will try to discuss in this particular lecture. The sum of the examples, so we will discuss. So, this is side channel spillway, then your side wear, then channel with permeable boundaries, then gutter for conveying storm water runoff, etc. So, these are some of the your example of spatially varied flow. So, now as I said that, so I can classify this your spatially varied flow basically into one is that spatially varied flow with increasing discharge. That means that is there is a addition of your water in the channel along with your distance, and another one is spatially varied flow with decreasing discharge. So, in the first case that is your spatially varied flow with increasing discharge. So, in that case an appreciable portion of the energy loss is due to the turbulent mixing of the added water and the water flowing into the channel. So, in this case what will happen that there will be turbulence, there is a and because of that there will be energy loss in the channel. So, this is in case of spatially varied flow with increasing discharge. So, in most of the cases the mixing is of relatively high magnitude and uncertainty. So, this is basically, so it is very difficult to your account that one. So, because of the resulting high and uncertain losses, the momentum equation is found to be more convenient than our energy equation. So, in this case what is happening that in the case of spatially varied flow with increasing discharge. So, there is a high energy loss, and therefore, the momentum equation. So, we will use momentum equation to derive the flow equation. So, we will use the momentum equation here, but in case of spatially varied flow with decreasing discharge. So, in that case the energy the energy equation is more suitable. So, in this case this type of spatially varied flow may be treated as a flow diversion, where diverted water does not have effect on the energy head. So, what is happening? So, in this case water is diverted from the channel and it does not have much effect on the energy head of the your flow. So, therefore, so in this type of your channel, so we will use energy equation to solve the problem. So, let us see the first part, that is spatially varied flow with increasing discharge. So, that we will discuss. So, we will derive the governing equation for this spatially varied flow with increasing discharge. So, in that case that water is added. So, this is a lateral spillway channel. So, here water is added to the channel, and in that case the flow discharge is increasing. Okay. So, as I said earlier, the significant loss of energy from mixing between the water entering the channel and the water flowing in the channel. So, there is a significant loss, and therefore, we cannot account that what will be the energy loss here. So, therefore, we are not using energy equation in this case. So, we are using the momentum equation, and the lateral flow enters the channel normal to the channel flow direction, causing considerable turbulence. So, therefore, we will here in this case we will use the momentum your conservation of momentum equation. So, these are the assumptions that with this actually we will derive the equation. So, assumptions are: the flow is unidirectional. So, here the flow is not unidirectional, but we are considering that flow is unidirectional. However, there is a strong cross current, as I said that there is a turbulent mixing. So, there is a strong cross current present in the form of spiral flow, particularly in lateral spillway channel, and the effect of this current and the accompanying turbulence cannot be evaluated easily. So, that is why we are considering. So, this is the first assumption, that flow is unidirectional. Okay. Then the second assumption is the pressure in the flow is hydrostatic. So, just like in gradually varied flow, in this case also we are considering the pressure in the flow is hydrostatic. So, that means flow is parallel to the bottom, but however, so this can be used, but however the flow at the outlet. So, in the outlet, that is the surface is curvilinear. So, in that case this is deviating from the assumption. So, in that case we have to apply some correcting factor. So, if there is when we are considering the curvilinear effect of the surface. Then another assumption is that slope of the channel is relatively small. So, that sin theta we can that tan theta we can consider sin theta. So, here the slope is considered slope of the channel is very small, and just like your gradually varied flow, that we are using Manning's formula here to evaluate the friction loss. So, this is flow of uniform flow equation. So, that we are using for evaluating the friction loss. And then the effect of air entrainment is negligible. So, this is another assumption, but if there is a significant air entrainment, so in that case we have to consider the correction, or we have to apply the correction here. So, but in this case what we will do, we will analyze first without considering the correction, and later on we will apply the correction. So, let us see how we can derive this governing equation. So, this figure shows a channel here. So, this is the channel here. So, the bottom slope of the channel is your S naught, and so we are considering two sections, that is your section 1 and section 2. So, depth of flow at section 1 is y1 and that of your section 2 is y2, and the pressure at section 1. So, this is the pressure at section 1, and this pressure is P1 here, and pressure at section 2 is P2. Okay. So, this is the pressure at section 1 and this is the pressure at section 2. Now, the weight of the water which is acting vertically. So, it has two components, one is normal component and then the component along the channel is W sin theta. Okay. So, when we will consider the conservation of momentum, so we will use W sin theta component. And so, this is and now and there is a Q star. So, Q star is nothing but this is your dq by dx, that means that is dq by dx is your Q star, that is the the amount the volume of water entering into the control volume. So, here. So, now this is the cross section here. So, this cross section is so we consider the trapezoidal section here. So, y1 is the depth at section 1 and depth at section 2 is y1 plus dy, and this is your dy, and then this is the CG of this particular section, and it is from the surface it is your z bar. Now, if we apply the conservation of momentum equation, so here this is the momentum equation can be written here between section 1 and section 2, that is your m2 minus m1 which is equal to p1 minus p2 plus w sin theta minus df. So, I can write it. So, this is nothing but your dm which is equal to p1 minus p2 plus w sin theta minus your friction loss, and this is also we can write it that this is dm by dx and dx. So, I can write this is p1 minus p2 plus w sin theta minus f. Okay. So, now we will try to calculate the component. So, what is your dm by dx, that I will then what is p1 minus p2, then w sin theta and minus ff. So, in this particular control volume, and once we will put it and simplify it, we will get the governing equation for spatially varied flow with increasing discharge. So, let us see the first part, that is your m2 minus m1. So, we will try to calculate what is m2 minus m1. So, before that the momentum flux can be written as, so momentum flux can be written as your beta. So, w by z qv. So, where w is the unit weight of water, q is the discharge and v is the velocity of flow. And I can write that V can be replaced by so this is your Q by A. So, in that case I can write beta W by Z Q square by A. Now, this as I said that m2 minus m1 which is equal to dm, and I can also write dm by dx into dx. So, I can write that. So, now if I take the derivative of this momentum, that is your this is nothing but this is your momentum. So, momentum is m equal to beta w by z q square by a. So, if I take, so basically I would like to calculate what is dm by dx. So, this is nothing but d by dx. So, this is w, so beta w by z and this is q square by a. Okay. So, now if I take the derivative of that one, so derivative of this, so I am getting this beta w by z. So, that is your constant. So, I am taking it out and then I am getting twice q by a. So, this is twice q by a dq by dx and then minus q square by a square, then dA by dy and dy by dx. So, I can write it. So, basically this is q square by a. So, this is dA by dx. So, I am writing dA by dy and dy by dx because finally I need to calculate what is dy by dx. So, now here this is your that q that dq by dx is nothing but your q star. So, I am writing this is dq by dx is your q star. So, that is the amount of our water what is entering into the control volume per unit distance, and q square by and dA by dy is your t. Okay. So in that case I am putting t here. So finally I am getting, this is the expression for dm. So dm is beta w by q within bracket 2q by a q star minus q square by a t dy by dx. Now let us calculate the component w sin theta. So here w is the weight of water in the control volume. So this is the total weight of water. So this is nothing but volume into your small w. So the component of w in the direction of flow. So as I said already that the component of flow in the direction of component of w in the direction of flow is w sin theta, and which can be written as this is small w within bracket, this is area. So this is the average area. So average area is A plus half of dA into dx. Dx is the length of the control volume into S naught. So S naught, as I said that, so I can write when theta is small, sin theta can be written as S naught. So then if I this line can be written as W S naught A dx plus W S naught half of dA dx, and as this value is small, so I can neglect this one, and if I do that, so finally I am getting W S naught A dx. So this component, that is your W sin theta is nothing but W S naught A your dx. So this is I am getting. And then as we have mentioned already that the friction head between section 1 and section 2 is equal to the friction slope multiplied by dx. So I can write it that HF equal to SF into dx. So SF I can calculate from the Manning's equation. So Manning's equation as we know already, that is 1 by n r 2 by 3 s half, and this I can write it, that is this is SF and this is SF. I can write this is v square into n square and r to the power 4 by 3. So this is SF. So I am putting SF here, and V I can replace. So if I replace V is equal to q by a, so I am getting q square n square divided by a square r to the power 4 by 3 into dx. So this is nothing but your HF. Now the friction force along the channel wall is equal to the pressure due to the friction head multiplied by the average area. So that I can write that FF, which is equal to W, this is the average area is A plus half dA into SF dx. So and in this case also I can write that this is plus this is half dASF dx. So if I neglect this thing, then I am getting FF equal to W, this is A SF dx. Okay. So I am getting this thing. Now let us see what is the pressure and on section 1. So pressure is this is W, that is the unit weight of water, into Z bar, that is the distance of centroid from the surface of the water. So as I have said earlier, so this is the surface and this is your Z bar. So this is the Z bar and into cross sectional area A. Okay. So this is the cross sectional area. This is your P1, that is the pressure at section 1. So where Z bar is the depth of the centroid. So this is the depth, this is CZ, this is your CZ, depth of the centroid, your depth of the centroid from the water surface. So this is your P1 which is equal to WZ bar A, and similarly I can also write I find out what is the pressure at section 2. So pressure at section 2 is P2, which is W. Now this is your dy. So this distance is your dy. So therefore I have to take the moment of this area and then moment of your dy. So, if I take the moment of your means section A, so in that case I am getting w z bar plus dy. So, now centroid is here. So, this is your z bar plus dy. So, z bar plus dy into A plus this is the moment of this. So, moment of this area is w, area is dA, and Cg here is your dy by 2. So, this is dy by 2. So, therefore, I can write it. So, if I neglect this part, so this part is because dA into dy is very small. So, I can do that. So, in that case I am getting w z bar plus dy into A. So, now if I calculate what is P1 minus P2, so P1 minus P2 is w z bar A. So, this is your w z bar A minus w z bar plus dy into A, and finally, I am getting w dy A. So, I am getting P1 minus P2, which is equal to w, that is unit weight of water, dy into A. So, I am getting. So, now I have calculated what is your dm. So, dm by dx. Okay. So, then I have calculated what is w sin theta, then I have calculated what is friction force, and finally, I have calculated what is P1 minus P2. So, if I put this value in the your momentum equation and simplify it, I will get the governing equation for spatially varied flow with increasing discharge. Okay. So, the momentum equation, as I said already. So, this is m2 minus m1 equal to P1 minus P2 plus w sin theta minus ff. So, I can write this is dm, which is equal to, so I am putting P1 minus P2, which is w dy A plus w sin theta can be written as w s naught A dx, and similarly ff can be written as w s f A dx. Okay. So, I can write it that dm by dx into dx, and now I can replace this term. So, this is the term I am replacing here, that is dm by dx into dx is nothing but beta w by z twice q by a q naught minus q square by a square t, this is dy by dx into dx, and which is equal to w dy a w s naught a dx minus w s f a dx. So, I can cancel this w, I can cancel from all these terms. So, w is cancelled, and then I can your cancel this area from here. So, a, then I have to take an area here. So, I am dividing this equation by a, and then I am also dividing this equation by dx. So, in that case I am getting this equation. So, this equation I am getting dividing this equation by a dx. So, this is I am getting beta by a zy within bracket twice q small q star by a minus q square t by a square dy by dx, and which is equal to, this is dy by dx. So, now I am dividing it by dx, then I am getting s naught minus s f. Okay. So, if I simplify it, so in that case this dy dx, and I am taking this term here. So, beta q square t by z a cube dy dx, and the other terms I am writing in the right hand side, which is equal to s naught minus s f minus twice beta q star divided by z a cube, and if I simplify it for dy by dx. So, finally, I am getting this equation. So, which is s naught minus s f minus twice beta q star divided by z a square and divided by 1 minus beta q square t by z a cube. Okay. So, this is the equation for your spatially varied flow with increasing increasing discharge. Okay. So, I am getting this equation. Now, if you recall that the gradually varied flow equation, that is the gradually varied flow equation was, that is dy by dx, which is S0 minus SF divided by 1 minus beta q square t by z a cube. So, what is the difference between ZVF and SVF with increasing discharge? So, we are getting an additional term, this term. So, what is this is twice beta q small q star divided by z a square. So, this is the additional term we are getting in case of gradually varied flow with increasing discharge. Now, let us see the governing equation for the spatially varied flow with decreasing discharge. So, in that case what will happen, the water is coming out from the channel. Okay. So, this is an example. So, where this is the main channel, and water is coming out of the channel. So, in that case what is happening? So, it is not disturbing the energy or not changing the energy of the energy of flow or energy of water. So, in that case, so we are using the energy equation to derive the your governing equation for spatially varied flow. So, the assumptions are here. The pressure distribution is hydrostatic, just like the other means when we derive the equation for increasing discharge. So, pressure distribution is hydrostatic. The one dimensional method of analysis is used here. So, we have used one dimensional. So, this is one dimensional only. So, as this is only in x direction. Then the energy correction factor, your alpha is used. So, we have used the energy correction factor, and then friction loss is calculated using Manning's formula. So, that and we are assuming that withdrawal of water does not have any effect on our energy content per unit mass of water in the channel. So, this is there may be some minor loss, but we can consider that this energy loss is minimum or negligible. So, we can consider that there is that withdrawal of water does not have a effect on our energy content per unit mass of water, and the flow is steady and the channel is prismatic, and the bottom and is of small slope. So, S naught is very small. So, with that, with this assumption, so let us write the energy equation. Suppose at any section, so energy equation, total energy I can write, that is H equal to Z. So, Z is the datum head, then the Y pressure, and alpha v square by twice Z is the kinetic energy. So, now if I differentiate with respect to x, so I can write dH by dx which is equal to dz by dx plus dy by dx plus d by dx, that is alpha your v square by twice z. So, in that case dH by dx is your minus SF and dz by dx your minus S naught. So, I can replace it, I can replace it here. So, I am writing that dH by dx equal to minus SF and dz by dx equal to minus S naught. Okay. So, this is dy by dx, and if I calculate the derivative of d by dx alpha v square by twice z. So, v can be written by q by a. So, in that case I am getting alpha q square by z a square, and if I take the derivative, this is alpha by twice z. So, this is constant. So, I am taking it out, and if I take the derivative, then twice q by a square dq by dx minus twice q square by a cube. So, dA by, so this is your dA by dx. So, but I am writing dA by dy and dy by dx. So, now dA by dy is t. Okay. So, this term is your t, and this is your q star. Okay. So, finally, I am getting this value, that is alpha by twice z. So, within bracket twice q star by a square minus twice q square t by a cube into dy dx. Okay. So, if I put this in this equation, so this part I am putting it here. So, then if I simplify it, so I am getting dy by dx, which is equal to S naught minus SF minus alpha capital Q small q star z a square divided by 1 minus alpha q square t by z a cube. Okay. So, this is the governing equation for spatially varied flow with decreasing discharge. So, in this case also, so I am getting this additional term. So, if I remove this term, so this will be, so if I remove it, then this will be the gradually varied flow equation. So, this will be the gradually varied flow equation. So, if I remove it and the difference with the spatially varied flow with increasing discharges. So, I will get another 2 here, and this is twice beta q star by z a square, and in case of spatially varied flow with decreasing discharge. So, this 2 is not there, and with gradually varied flow. So, if I remove this part, then this equation will become your gradually varied flow equation. So, now let us see that I would like to solve one example problem. So, this is a spatially varied flow example problem with decreasing discharge. So, in that case discharge is decreasing. So, let us read the problem. The problem here is 11 cubic meters per second are diverted through pores on the bottom of a channel between section 1 and section 2. So, what does it mean? That 11 cubic meter of water has been diverted from the channel bottom and through the pores of the channel bottom between section 1 and section 2. So, this figure is showing here. So, this is your section 1 and section 2. So, between section 1 and section 2, 11 cubic meter of water has been diverted. Okay. The channel bottom is horizontal. So, here this is S naught is your 0. So, okay. So, channel bottom is horizontal. So, there is channel slope is 0, and channel width is your channel width is 4.5 meters. So, that means that B equal to 4.5 meter. Okay. So, this is your B. Then depth of flow at section 1. So, y1, that means here. So, this is the depth of flow. So, this is the depth of flow at section 1, this is y1, and y1 is your 2.4. So, 2.4, and flow at section 1, that is q equal to q1 is 33 meter cube per second. So, here this is the q1, so which is 33 meter cube per second. So, the problem is calculate the depth of flow at section 2. So, this has to be calculated. What is the value of y2? So, we have to calculate what is the depth of flow at section 2, and there is another question, what channel width at section 2 would be required to produce a depth of your 2.5 meters. So, right now the channel width is, that is your B1 equal to 4.5, and here also it is 4.5. So, this is B2, but the problem is telling that if the Y2, so if the Y2 is 2.5, then what should be the value of your B2? So, this is another question. So, we have to find out the value of B2 in that case, and so the head loss is your neglected. So, we should there is no head loss, okay, between your section 1 and section 2. So, let us solve this problem. So, now in this case, this is a spatially varied flow problem with decreasing discharge. So, that means the discharge is decreasing between section 1 and section 2. So, if the discharge at section 1 is 33, so 11 cubic meter has been diverted between section 1 and section 2. So, therefore, the Q2 will be your 22 meter cube per second. Okay. So, in that case, so we that energy, as I said that, so we will apply the energy equation here, and energy at section 1 and section 2 will be equal. So, let us solve the problem. So, the solution. So, this is a problem of spatially varied flow with decreasing discharge. So, with decreasing discharge, as such the specific energy remains constant. Okay. So, specific energy constant. So, therefore, I can write the specific energy. So, E1 equal to E2. So, what is E1? So, E1 is Y1 plus V1 square by twice Z, which is equal to E2, and which is equal to Y2 plus V2 square by twice Z. Okay. So, I can write this like this. So, this is your Y1. So, V1 I can write that small q1 by Y1. So, this is square and divided by twice Z, and which is equal to Y2 plus q2 square by Y2. So, whole square and divided by. So, now let us calculate what is q1. So, q1 is capital Q1 by B1. So, which is equal to 33 divided by 4.5, and which is equal to 7.33 meter cube per second per meter. Okay. So, similarly, I can calculate what is Q2. So, Q2 is small q2 is capital Q2 by B2. So, in that case this is 22 by 4.5, and which is equal to 4.89 meter cube per second per meter. Okay. So, now let us calculate the Froude number to see whether flow is subcritical, supercritical or critical. So, let us calculate Froude number. So, Froude number is given by Fr equal to V by this is Zy1. So, I can write it like that. So, this is Q1 by Y1 and under root Zy1. So, if you put the value, this is 7.33 divided by 2.4 and under root 9.81 into 2.4. So, this is I am getting the value of 3.05 and divided by 4.85, and which is equal to 0.629. Okay. So, here this is less than 1. So, therefore, the flow is subcritical. Okay. The flow is subcritical here, and Froude number value is 0.629, and which is your less than 1, and therefore, the flow is subcritical. So, now I would like to calculate what is the value of Y2. So, in this case, as I said that this E1 is equal to E2. So, therefore, I can write this is Y1 plus V1 square by twice Z is equal to Y2 plus V2 square by twice Z. Okay. So, and this is equal to, so this is equal to, this is Y1 plus this is q1 by y1 whole square 1 by twice g, which is equal to y2 plus q2 by y2 whole square 1 by twice g. Okay. So, put the value of y1. So, y1 is 2.4 and plus this is q1 is 7.33, then y1 is 2.4 whole square into 2 into 9.81 and which is equal to y2 plus this is 1 by y2 square and this is q square. So, q is 4.89 square divided by twice g, and so if I calculate it, so I should get 2.875. So, this is your E1, that is the specific energy, which is equal to Y2 plus 1.218 divided by Y2 square. So, now I can solve it. So, I can solve this equation. So, I use trial and error method. So, if I solve it, so I am getting the value of y. So, I am getting two values. So, there are two roots of this equation, that is your 0.758 and 2.709. So, I am getting two depths, that is your one is 0.758 and another one is 2.709. So, let us draw the specific energy diagram here. So, we have already learned these things. So, this is the specific energy diagram. So, this is your 45-degree line, and so I have two q small q. So, this is your okay, and there is another one. Okay. So, here this is for q1. So, this is for q1, which is equal to 7.33 meter cube per second per meter, and this is for q2, that is your 4.89. Okay. So, I am getting this is for q1. So, here q1 is greater than q2, and now somewhere here this is the specific energy. So, energy is constant here, this is E equal to 2.875 meter. So, this is the specific energy. So, here the discharge at section 1 is your the specific discharge, that means discharge per unit weight is 7.33 at section 1. So, therefore, this is your section 1. So, therefore, this depth must be, this is your y1. So, this depth is y1, which is equal to your 2.4. So, it is given. So, it is given and that is 2.4 meter. So, now what is happening? The specific discharge is decreasing from section 1 to section 2, and section 2 the specific discharge is 4.89. So, in that case, so the depth has to increase here. So, this is the depth, new depth, and which should be equal to, this is your y1, this is y2, and so which is equal to your 2.709. Okay. So, this is your 2.709. So, in that case the depth is increasing, and this is basically, this is in your subcritical flow. Okay. So, in this case, as it is in subcritical flow, so in this case the depth of flow is increasing. So, from 2.4 to 2.709, but in case of supercritical flow, if it would have been in supercritical flow, in that case the depth of flow will your decrease. So, this is the section 1 and this will be at section 2. Okay. So, that would have been. So, but in this case this is subcritical. So, therefore, depth is increasing. So, the solution is, this is your solution. So, solution is the y2 will be 2.709. Okay. Now, let us see the other part of the problem. So, other part is telling that if we would like to maintain a depth of y 2, suppose y 2 equal to 2.5. Okay. So, here, so now if we want to maintain a depth of 2.5 at section 2. So, that means y 2 will be 2.5. So, therefore, I can write it that E, which is equal to y 2 plus v 2 square by twice g. So, energy is constant. So, energy we know that is your 2.875. Okay. So, this is nothing but y 2 plus. So, I can write it that V 2 is Q 2 by A 2 square, okay, divided by twice z, and which is equal to y 2 and plus. So, Q 2 by A 2 means B 2 y 2. Okay. So, this is square by twice z, and I can write it that this is y 2 plus this is q square b 2 square y 2 square 1 by twice z. So, if I put the value, so here E is 2.875. So, which is equal to y 2 is 2.5. So, this is we have to maintain at section 2, plus this is 22 square, capital Q is 22, then this is B 2 square into y 2 is 2.5 square into 1 by 2 into 9.81. Okay. So, if I solve it, so I should get this is 3.946 divided by B 2 square, which is equal to 2.875 minus 2.5, and B 2 square is equal to 3.946 divided by 0.3758, which is equal to 10.501. And if I solve it for B 2, so I am getting 3.24 meter. So, this is the solution. So, that means if I reduce the width of the channel to 3.24, in that case the depth of flow at section 2 will be 2.5. So, to maintain a depth of flow of 2.5 at section 2, so I have to reduce the width of the channel to 3.24. So, earlier it was 4.5 and now we have to reduce it to 3.24.